Deep in the heart of the Virgo cluster, over 50 million light-years away, lies a galaxy that defies imagination. Messier 87, a colossal giant, is not just another galaxy. It is a cosmic enigma, home to some of the most bizarre and mysterious objects ever discovered. At its core, a supermassive black hole, so massive it bends the very fabric of space and time, dominates the scene. But that is just the beginning. Surrounding this cosmic beast are strange filaments of gas, ghostly galaxies, and stars moving at unimaginable speeds. What secrets do these objects hold? What can they tell us about the universe we live in? In this video, we will uncover 25 of the strangest objects within Messier 87, each one more fascinating than the last. From the invisible grip of dark matter to the explosive remnants of ancient stars, prepare to journey into a galaxy that challenges everything we thought we knew about the cosmos. Stay with us because by the end of this video, you will see the universe in a whole new light. Now, let's turn our attention to the most iconic feature of Messier 87, the supermassive black hole at its heart. This cosmic giant is not just any black hole, it's a behemoth weighing in at an astonishing 6.5 billion times the mass of our Sun. To put that into perspective, if you could place this black hole in our solar system, its event horizon would stretch far beyond the orbit of Pluto. But what truly sets this black hole apart is the groundbreaking achievement of capturing its image. In 2019, the Event Horizon Telescope collaboration unveiled the first ever photograph of a black hole, revealing a glowing ring of light surrounding a dark shadow. This historic image not only confirmed the existence of black holes, but also gave us a glimpse into the extreme physics at play near these mysterious objects. The supermassive black hole in Messier 87 doesn't just sit quietly. It actively shapes its surroundings. Its immense gravity pulls in gas, dust, and even stars, creating a swirling disk of superheated material that emits intense radiation. This process not only powers the galaxy's most energetic phenomena, but also influences the movement and behavior of stars and gas clouds throughout Messier 87. In many ways, this black hole is the unseen architect of the galaxy, dictating its structure and evolution over billions of years. As we continue our journey through Messier 87, we'll see how this colossal black hole is just the beginning of the galaxy's many mysteries. Now, shifting our gaze from the supermassive black hole itself, let's zoom in on one of its most dramatic features, the relativistic jet. This incredible jet is a stream of particles and energy that shoots out from the black hole at nearly the speed of light. To give you an idea of just how fast that is, imagine traveling from Earth to the Moon in less than 2 seconds. That's the kind of speed we're talking about here. But what makes this jet truly fascinating is how it interacts with the space around it. As the jet blasts through the galaxy, it collides with gas and dust, creating shock waves that light up the surrounding area. These interactions produce some of the most stunning visual phenomena in the universe, including glowing filaments and massive bubbles of hot gas. Scientists believe that the jet is powered by the black hole's magnetic fields, which twist and channel the energy from the swirling disk of matter around it. This process not only fuels the jet, but also helps regulate the black hole's growth and influence on the galaxy. The relativistic jet is a testament to the raw power of Messier 87 black hole, and it serves as a reminder of just how dynamic and energetic the universe can be. As we move forward, we'll uncover even more strange and awe-inspiring objects hidden within this galaxy. Now, let's turn our attention to something you can't see, but whose presence is impossible to ignore: the dark matter halo surrounding Messier 87. This invisible yet colossal structure is one of the most mysterious and influential features of the galaxy. Unlike the stars, gas, and dust we can observe, dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. But don't let its elusive nature fool you. Dark matter is incredibly massive, and its gravitational pull is what holds Messier 87 together. Without it, the galaxy would simply fly apart. The dark matter halo extends far beyond the visible edges of Messier 87, enveloping the galaxy in a vast, unseen web. Its gravitational effects are profound, shaping the orbits of stars and influencing the movement of gas and dust. Scientists estimate that dark matter makes up about 85% of the galaxy's total mass, meaning it's the dominant force at play here. This invisible halo also plays a key role in the galaxy's evolution, acting as a cosmic scaffold that guides the formation of stars and the growth of the supermassive black hole at its center. But how do we know dark matter exists if we can't see it? The answer lies in its gravitational influence. By observing how stars and gas move within Messier 87, astronomers can detect the gravitational tug of dark matter, even though it remains hidden from view. This invisible halo isn't just a passive observer. It actively shapes the galaxy's structure, creating the conditions for the stunning phenomena we've already explored, like the relativistic jet and the supermassive black hole. As we continue our journey through Messier 87, we'll uncover even more strange and fascinating objects, each revealing a new layer of this galaxy's complex and dynamic nature. But for now, let's marvel at the unseen force that holds it all together, the dark matter halo, a silent yet powerful architect of the cosmos. Now, let's shift our gaze to a dazzling spectacle that surrounds Messier 87, a swarm of thousands of globular clusters. These dense, spherical collections of stars are like ancient time capsules, orbiting the galaxy and holding secrets to its past. Unlike the stars scattered throughout the galaxy, globular clusters are tightly packed, with hundreds of thousands or even millions of stars bound together by gravity. They form a glittering halo around Messier 87, adding to its majestic appearance. What makes these clusters so fascinating is their age. Many of them are among the oldest objects in the universe, dating back to when the galaxy itself was just beginning to take shape. By studying their composition, astronomers can piece together the early history of Messier 87. These clusters are rich in older, metal-poor stars, which tell us about the conditions of the universe billions of years ago. They're like cosmic fossils, preserving the chemical makeup of the early cosmos. But the globular clusters aren't just relics of the past, they also play a role in the galaxy's present. Their orbits around Messier 87 are influenced by the galaxy's gravity, including the dark matter halo we discussed earlier. By tracking their movements, scientists can map the distribution of dark matter and better understand how it shapes the galaxy. Some clusters even pass close to the supermassive black hole at the center, offering clues about its immense gravitational pull. The sheer number of globular clusters around Messier 87 is another striking feature. While our Milky Way has around 150 of these clusters, Messier 87 boasts thousands. This abundance suggests that the galaxy has a turbulent history, possibly formed through the collision and merging of smaller galaxies. Each cluster is a piece of the puzzle, helping us reconstruct the story of how Messier 87 grew into the giant we see today. As we marvel at these ancient star clusters, we're reminded of the intricate connections between the past and present in the cosmos. They're not just beautiful to observe, they're vital to understanding the life and evolution of Messier 87. And with that, let's move on to another extraordinary feature of this galaxy, where even more mysteries await. Now, let's turn our attention to one of the most defining features of Messier 87, its giant elliptical shape. Unlike the familiar spiral arms of galaxies like our Milky Way, Messier 87 presents a smooth, oval-like structure that sets it apart in the cosmic landscape. This elliptical form isn't just a matter of appearance, it holds profound clues about the galaxy's history and how it came to be. Elliptical galaxies like Messier 87 are often described as cosmic giants, and for good reason. They lack the swirling arms and star-forming regions that characterize spiral galaxies, instead appearing as vast, diffuse collections of stars. This smooth, almost featureless shape is a result of their formation process. Unlike spiral galaxies, which often form from the gradual accumulation of gas and dust, elliptical galaxies are thought to emerge from violent collisions and mergers between smaller galaxies. These cosmic crashes disrupt the delicate structures of spiral arms, leaving behind a more uniform, rounded shape. Messier 87 elliptical form also tells us about its age and evolution. The stars within it are predominantly old, with fewer young, hot stars compared to spiral galaxies. This suggests that Messier 87 has largely exhausted its gas supply, limiting the formation of new stars. Over billions of years, the galaxy has settled into a stable, almost serene state, with its stars orbiting in a more random, less organized fashion than those in spiral galaxies. Another striking difference lies in the galaxy's environment. Messier 87 resides at the heart of the Virgo cluster, a dense gathering of galaxies. This crowded setting likely played a significant role in shaping its elliptical form. Frequent interactions and mergers with neighboring galaxies over eons would have stripped away gas and dust, preventing the formation of spiral arms and contributing to its smooth, rounded appearance. The sheer size of Messier 87 elliptical shape is also worth noting. It spans hundreds of thousands of light years, making it one of the largest galaxies in the observable universe. Its immense gravitational influence extends far beyond its visible boundaries, shaping the surrounding cosmic environment and even influencing the orbits of smaller galaxies nearby. Understanding Messier 87 elliptical shape gives us a glimpse into the dynamic processes that govern galaxy formation and evolution. It's a testament to the power of cosmic collisions and the relentless pull of gravity, shaping the universe on a scale that's almost beyond comprehension. And as we continue our journey through this extraordinary galaxy, we'll uncover even more of its secrets, each one adding to the awe-inspiring story of Messier 87. Now, let's venture closer to the heart of Messier 87, where something truly enigmatic awaits: the mysterious filaments of gas and dust. These delicate, thread-like structures stretch across the galaxy's core, weaving a complex tapestry that has puzzled astronomers for decades. Unlike the smooth, uniform appearance of the galaxy's outer regions, these filaments are intricate and chaotic, hinting at the dynamic processes unfolding near the supermassive black hole. These filaments are not just random wisps of material, they play a crucial role in the galaxy's ecosystem. Composed primarily of ionized gas and dust, they are thought to be the remnants of past cosmic events, possibly the aftermath of collisions or the expulsion of material from the black hole itself. Some astronomers believe these filaments are the result of powerful magnetic fields interacting with the surrounding gas, shaping it into these elongated forms. Others suggest they could be the product of shock waves generated by the black hole's intense gravitational pull, compressing and stretching the gas into these striking patterns. One of the most fascinating aspects of these filaments is their connection to the black hole's feeding process. As material spirals toward the black hole, it doesn't fall in directly. Instead, it forms an accretion disk, a swirling, superheated ring of gas and dust. The filaments appear to act as conduits, channeling material from the outer regions of the galaxy into this disk. In a sense, they are like cosmic rivers, guiding the flow of matter toward the black hole's insatiable appetite. This process not only fuels the black hole, but also powers some of the galaxy's most energetic phenomena, including the relativistic jet we discussed earlier. But the filaments are more than just fuel lines, they also serve as a record of the galaxy's history. By studying their composition and structure, astronomers can piece together the events that shaped Messier 87 over billions of years. For instance, the presence of certain elements within the filaments can reveal the types of stars that once existed in the region. while their arrangement provides clues about the forces that have acted upon them. It's like reading a cosmic diary, with each filament telling a story of creation, destruction, and transformation. What makes these filaments even more intriguing is their resilience. Despite the extreme conditions near the black hole, intense radiation, powerful magnetic fields, and gravitational forces that can tear matter apart, the filaments persist. This suggests that they are constantly being replenished, either by new material flowing into the galaxy's center or by processes within the filaments themselves that allow them to maintain their structure. As we continue to unravel the mysteries of these filaments, one thing is clear: they are a vital piece of the puzzle in understanding how Messier 87 operates. They remind us that even in the most chaotic and extreme environments, there is order and purpose. And as we move forward in our exploration of this incredible galaxy, we'll encounter even more wonders that challenge our understanding of the universe. Now, shifting our gaze to the outskirts of Messier 87, we encounter a phenomenon that seems almost otherworldly: the ultra-diffuse galaxies. These faint, ghostly structures are unlike the bright, densely packed galaxies we often imagine. Instead, they are incredibly dim and spread out, making them some of the most elusive objects in the cosmos. Imagine trying to spot a faint wisp of smoke against a dark night sky. That's the challenge astronomers face when studying these enigmatic galaxies. Ultra-diffuse galaxies are characterized by their extremely low density. While they can be as large as our own Milky Way, they contain far fewer stars, sometimes only 1% of the stellar population. This sparse distribution of stars makes them nearly invisible against the backdrop of space, requiring some of the most advanced telescopes and imaging techniques to detect them. Their faint glow often blends into the surrounding darkness, leaving them hidden in plain sight. But why are these galaxies so faint? One theory suggests that they may have formed in regions of the universe where matter was less concentrated, resulting in fewer stars being born. Another possibility is that they lost much of their gas and dust over time, either through interactions with other galaxies or through internal processes that prevented new stars from forming. Without the bright, young stars that illuminate typical galaxies, ultra-diffuse galaxies remain shrouded in mystery. Despite their faintness, these galaxies play a crucial role in our understanding of galactic evolution. Their low density and unique properties challenge our assumptions about how galaxies form and evolve. For instance, some ultra-diffuse galaxies appear to have an unusually high amount of dark matter, the invisible substance that makes up most of the universe's mass. This raises questions about how dark matter is distributed and how it influences the structure of galaxies. One of the most intriguing aspects of ultra-diffuse galaxies is their resilience. Despite their faint appearance, many of these galaxies have survived for billions of years, enduring the gravitational pull of larger galaxies like Messier 87. Some even show signs of having avoided major collisions or disruptions, preserving their delicate structures over cosmic timescales. This makes them valuable time capsules, offering insights into the early universe and the conditions under which galaxies first formed. As we continue to study these ghostly galaxies, they remind us that the universe is full of surprises. They challenge our understanding of what a galaxy can be and push the boundaries of our observational capabilities. And as we move forward in our exploration of Messier 87, we'll uncover even more wonders that defy our expectations and deepen our appreciation for the vast, mysterious cosmos. Now, let's turn our attention to the heart of Messier 87, where the galaxy's supermassive black hole exerts its immense gravitational pull. Here, we find a group of stars that defy our everyday understanding of motion, the fast-moving stars. These celestial bodies zip through space at astonishing speeds, some reaching velocities of thousands of kilometers per second. To put that into perspective, imagine a star racing across the sky faster than a bullet fired from a gun. This incredible speed is a direct result of the black hole's overwhelming gravity, which warps the fabric of space-time and accelerates these stars to such extreme velocities. The trajectories of these stars are equally fascinating. Instead of following the gentle, elliptical orbits we see in most star systems, these stars trace tight, chaotic paths around the black hole. Some swing perilously close to the event horizon, the point of no return, before being flung outward in a cosmic slingshot effect. Others spiral inward, gradually losing energy until they are consumed by the black hole. These dynamic movements provide astronomers with a unique opportunity to study the effects of extreme gravity in action. What makes these fast-moving stars so valuable to science is the information they reveal about the black hole itself. By observing their speeds and paths, researchers can calculate the mass of the black hole with remarkable precision. In fact, it was the motion of these stars that first provided strong evidence for the existence of supermassive black holes in the centers of galaxies. The faster a star moves, the stronger the gravitational force acting upon it, and the more massive the black hole must be. This relationship has allowed scientists to confirm that Messier 87 black hole weighs in at a staggering 6.5 billion times the mass of our Sun. But the story doesn't end there. These stars also offer clues about the environment near the black hole. Their movements reveal the presence of intense magnetic fields, swirling clouds of gas, and other phenomena that shape the region. Some stars even pass through the black hole's accretion disk, the swirling ring of matter that feeds the black hole, creating bursts of light and radiation that can be detected from Earth. These interactions provide a rare glimpse into the chaotic and energetic processes at work in the heart of a galaxy. As we continue to study these fast-moving stars, they remind us of the incredible forces at play in the universe. They challenge our understanding of gravity, motion, and the very nature of space and time. And as we move forward in our exploration of Messier 87, we'll uncover even more secrets hidden within this cosmic powerhouse, deepening our appreciation for the wonders of the cosmos. Now, let's shift our gaze outward from the chaotic dance of fast-moving stars near Messier 87 black hole to something even more expansive, the galaxy's colossal radio lobes. These enormous structures stretch far beyond the visible boundaries of Messier 87, reaching hundreds of thousands of light years into the surrounding intergalactic space. But what exactly are these radio lobes and how do they come to be? The answer lies in the powerful relativistic jet we explored earlier, which acts as a cosmic engine, propelling energy and matter outward at nearly the speed of light. As the jet blasts through the galaxy, it doesn't just disappear into the void. Instead, it collides with the thin gas that fills the space between galaxies, creating shock waves that heat the gas and cause it to emit radio waves. Over time, this process forms the massive lobes we observe today. These lobes are essentially giant reservoirs of energy, storing the power unleashed by the black hole and its jet. They glow brightly in radio wavelengths, making them a striking feature of Messier 87 when viewed through radio telescopes. The impact of these radio lobes on their surroundings is profound. As they expand, they push against the intergalactic medium, the sparse gas that exists between galaxies. This interaction can trigger the formation of new stars in nearby galaxies or even disrupt existing star-forming regions. The lobes also act as cosmic accelerators, speeding up particles to incredibly high energies and producing cosmic rays that travel across the universe. These particles can influence the evolution of galaxies far beyond Messier 87 itself. What's truly remarkable is how these radio lobes serve as a record of the black hole's activity over millions of years. By studying their size, shape, and structure, astronomers can piece together the history of the relativistic jet and the bursts of energy it has released. Some lobes show signs of older, faded activity, while others appear bright and energetic, indicating recent outbursts from the black hole. This layered history provides a unique window into the dynamic life cycle of supermassive black holes and their influence on the cosmos. As we marvel at the scale and power of Messier 87 radio lobes, we're reminded of the interconnected nature of the universe. These structures are not just isolated phenomena, they are part of a vast cosmic web, shaping and being shaped by the environment around them. And as we continue our journey through the strange and wondrous objects within Messier 87, we'll uncover even more ways this galaxy challenges our understanding of the universe. Now, let's turn our attention to another fascinating feature of Messier 87, the mysterious X-ray hotspots scattered throughout the galaxy. These regions are not just random blips of energy, they are intense sources of X-ray emissions, revealing some of the most extreme environments in the universe. But what exactly are these hotspots, and why do they glow so brightly in X-rays? The answer lies in the interplay between the supermassive black hole at the galaxy's center and the surrounding matter. These X-ray hotspots are often found near the base of the relativistic jet, where the black hole's immense gravitational pull and magnetic fields accelerate particles to incredible speeds. As these particles collide and interact, they release bursts of X-ray energy, creating the bright hotspots we observe. These emissions are so powerful that they can outshine entire galaxies in X-ray wavelengths, making them a key focus for astronomers studying high-energy processes. But the story doesn't end there. These hotspots also provide critical clues about the black hole's feeding habits. As matter spirals toward the black hole, it heats up to millions of degrees, emitting X-rays in the process. By studying the distribution and intensity of these hotspots, scientists can map out the flow of matter around the black hole and understand how it fuels the relativistic jet. This, in turn, helps us piece together the complex relationship between the black hole and its surroundings. What's truly remarkable is how these X-ray hotspots act as cosmic laboratories, allowing us to study physics under conditions that are impossible to replicate on Earth. The extreme temperatures, magnetic fields, and particle speeds found in these regions push the boundaries of our understanding of high-energy astrophysics. They reveal how black holes can act as cosmic engines, converting gravitational energy into powerful bursts of radiation that shape the evolution of galaxies. As we explore these X-ray hotspots, we're reminded of the incredible diversity of phenomena within Messier 87. From the colossal radio lobes to the fast-moving stars and now these high-energy regions, each object tells a unique story about the forces at work in this galaxy. And as we continue our journey, we'll uncover even more ways Messier 87 challenges our understanding of the universe, one strange object at a time. Now, shifting our gaze to the outskirts of Messier 87, we encounter a phenomenon that speaks volumes about the galaxy's violent past, the tidal streams. These ghostly ribbons of stars and gas are the remnants of smaller galaxies that ventured too close to Messier 87's immense gravitational pull. Over time, these unfortunate galaxies were stretched and torn apart, their material scattered into long, flowing streams that now orbit the larger galaxy like cosmic scars. But what makes these tidal streams so fascinating, and what do they tell us about the life cycle of galaxies? Tidal streams are more than just remnants of destruction. They are a testament to the process known as galactic cannibalism. As Messier 87 gravity pulls in smaller galaxies, it doesn't just consume them whole. Instead, it strips them apart layer by layer, leaving behind these delicate trails of stars and gas. This process is a slow but relentless one, taking millions or even billions of years to complete. By studying these streams, astronomers can piece together the history of Messier 87 growth, revealing how it has grown larger by devouring its smaller neighbors. What's particularly intriguing about these tidal streams is how they act as cosmic fingerprints. Each stream carries clues about the original galaxy it came from, such as its age, composition, and even its trajectory before being torn apart. By analyzing the light from these streams, scientists can determine the types of stars and gas they contain, offering a glimpse into the building blocks of galaxies. This, in turn, helps us understand how galaxies like Messier 87 evolve over time, growing not just through the birth of new stars but also through the absorption of others. But the story doesn't end with destruction. These tidal streams also play a role in shaping the future of Messier 87. As the streams gradually merge with the larger galaxy, they contribute fresh material that can fuel new star formation. In this way, galactic cannibalism isn't just about destruction, it's also a process of renewal, ensuring that Messier 87 continues to thrive and evolve. As we examine these tidal streams, we're reminded of the dynamic and often violent nature of the universe. They serve as a vivid reminder that galaxies are not static entities but ever-changing systems, shaped by the forces of gravity and time. And as we continue our exploration of Messier 87, we'll uncover even more ways this galaxy challenges our understanding of the cosmos, one strange object at a time. Now, as we venture closer to the heart of Messier 87, we encounter a phenomenon that is both mysterious and essential to the galaxy's life cycle: the cold gas clouds. These dense, frigid clouds of gas hover near the galaxy's center, acting as the raw material for one of the universe's most fundamental processes, star formation. But how do these cold gas clouds form, and what role do they play in the chaotic environment surrounding the supermassive black hole? Cold gas clouds are like cosmic nurseries, providing the fuel needed to birth new stars. In the case of Messier 87, these clouds are found in the turbulent region near the galaxy's center, where the black hole's immense gravity and the relativistic jet create a dynamic and often hostile environment. Despite these challenges, the cold gas clouds persist, their temperatures dropping to just a few degrees above absolute zero. This extreme cold allows the gas to clump together, forming dense pockets that can eventually collapse under their own gravity, igniting the process of star formation. But the journey of these gas clouds is far from straightforward. As they drift closer to the black hole, they are subjected to intense forces. The black hole's gravity pulls at the clouds, while the relativistic jet blasts them with high-energy particles. These interactions can tear the clouds apart, heating the gas and preventing it from collapsing into stars. Yet, in some cases, the clouds manage to survive, their cold cores shielded from the surrounding chaos. When this happens, they become the birthplaces of new stars, adding to the galaxy's stellar population. What makes these cold gas clouds particularly fascinating is their dual role in the galaxy's ecosystem. On one hand, they contribute to the creation of new stars, ensuring that Messier 87 continues to evolve and grow. On the other hand, they also interact with the black hole, feeding it with material that powers its energetic processes. This delicate balance between creation and consumption is a key feature of the galaxy's central region, highlighting the interconnected nature of its components. By studying these cold gas clouds, astronomers gain valuable insights into the conditions necessary for star formation, even in the most extreme environments. They also learn more about how black holes influence their surroundings, shaping the fate of the gas and stars that come too close. As we continue to explore Messier 87, these cold gas clouds remind us of the intricate dance between creation and destruction that defines the cosmos, offering a glimpse into the forces that drive the evolution of galaxies. Now, shifting our gaze to the remnants of ancient cosmic explosions, we uncover another layer of Messier 87-rich history, the supernova remnants. These ghostly echoes of once massive stars tell a story of destruction and creation, offering a window into the galaxy's past and its ongoing evolution. Scattered throughout Messier 87, these remnants are the aftermath of supernova, the cataclysmic deaths of stars that once shone brightly before ending their lives in spectacular fashion. When a massive star exhausts its nuclear fuel, it collapses under its own gravity, triggering a violent explosion that can outshine an entire galaxy for a brief moment. This explosion scatters the star's outer layers into space, leaving behind a glowing shell of gas and dust, a supernova remnant. Within Messier 87, these remnants are not just relics of the past, they are active contributors to the galaxy's chemical makeup. As the remnants expand, they enrich the surrounding space with heavy elements like iron, oxygen, and silicon, forged in the hearts of the stars and released during the explosion. These elements are the building blocks of new stars, planets, and even life itself. Without supernova, the universe would lack the diversity of elements necessary for the complex structures we see today. In Messier 87, the remnants of these ancient explosions mingle with the galaxy's gas and dust, seeding the environment with the raw materials needed for future generations of stars and planetary systems. This process of cosmic recycling is a testament to the interconnectedness of the universe, where the death of one star gives rise to the birth of countless others. But supernova remnants are more than just chemical factories. They also serve as cosmic laboratories, allowing astronomers to study the physics of extreme events. The shock waves generated by supernova can accelerate particles to nearly the speed of light, creating cosmic rays that ripple through the galaxy. These remnants also emit radiation across the electromagnetic spectrum, from radio waves to X-rays, providing valuable data about the conditions within and around them. By analyzing this radiation, scientists can piece together the history of the supernova, the properties of the original star, and the impact of the explosion on its surroundings. In Messier 87, the presence of supernova remnants adds another layer of complexity to the galaxy's dynamic environment. They interact with the galaxy's magnetic fields, the relativistic jet, and even the black hole itself, creating a tapestry of influences that shape the galaxy's evolution. As we continue to explore these remnants, we gain a deeper understanding of the forces that drive the life cycles of stars and galaxies, reminding us that even in destruction there is creation, and in chaos there is order. Next, we'll turn our attention to another fascinating feature of Messier 87, the ultra-massive stars that burn brightly but briefly, leaving their mark on the galaxy in ways that are as dramatic as they are fleeting. Now, let's turn our attention to one of the most dazzling yet fleeting phenomena in Messier 87, the ultra-massive stars. These stellar giants are the rock stars of the galaxy, burning with an intensity that defies imagination but living lives that are tragically short. Unlike the stars we're familiar with, ultra-massive stars are true cosmic anomalies, packing hundreds of times the mass of our Sun into a single luminous body. Their sheer size and energy output make them some of the brightest objects in the galaxy, but their brilliance comes at a cost, a lifespan measured in mere millions of years, a blink of an eye in cosmic terms. The life of an ultra-massive star is a race against time. From the moment they ignite, these stars burn through their nuclear fuel at an astonishing rate, driven by the immense pressure and heat at their cores. This rapid consumption of fuel leads to a series of dramatic events, including the fusion of heavier elements like carbon, oxygen, and even iron. But this process can't last forever. Once the core can no longer sustain fusion, the star faces an inevitable and catastrophic end, a supernova explosion so powerful it can outshine entire galaxies. What makes these stars particularly fascinating is not just their explosive deaths but the legacy they leave behind. When an ultra-massive star goes supernova, it doesn't just vanish, it scatters its enriched material across the galaxy, seeding the cosmos with the heavy elements necessary for the formation of new stars, planets, and even life. In Messier 87, the remnants of these titanic explosions mingle with the galaxy's gas and dust, contributing to the ongoing cycle of stellar birth and death. Without these ultra-massive stars, the galaxy would lack the diversity of elements needed to create the complex structures we see today. But the story doesn't end there. In some cases, the core of an ultramassive star collapses into a black hole, adding to the galaxy's population of these mysterious objects. This process not only shapes the galaxy's structure, but also influences its evolution, as the black holes formed from these stars can grow over time, merging with others or feeding on surrounding matter. In Messier 87, the presence of ultramassive stars adds another layer of intrigue to the galaxy's dynamic environment, reminding us that even the brightest stars are destined to fade, leaving behind a legacy that shapes the cosmos for eons to come. As we move forward, we'll explore another fascinating aspect of Messier 87, the dwarf galaxy companions that orbit this cosmic giant, playing a crucial role in its evolution and the intricate dance of galactic interactions. Now, let's shift our gaze to the smaller cosmic neighbors that dance around Messier 87, the dwarf galaxy companions. These tiny galaxies, though often overlooked, play a vital role in the grand story of Messier 87 evolution. Orbiting the colossal elliptical galaxy like satellites, these dwarf galaxies are more than just cosmic bystanders. They are active participants in shaping the destiny of their larger counterpart. Dwarf galaxies are much smaller and less massive than Messier 87, but what they lack in size, they make up for in influence. Over billions of years, these galaxies have interacted with Messier 87 through gravitational tugs and occasional collisions. These interactions can strip away gas and stars from the dwarf galaxies, feeding Messier 87 growth and contributing to its vast halo of stars and dark matter. In some cases, the gravitational pull of Messier 87 can even tear apart these smaller galaxies, leaving behind streams of stars and gas that weave through the larger galaxy like cosmic ribbons. But the relationship isn't one-sided. While Messier 87 often dominates these interactions, the dwarf galaxies also leave their mark. As they orbit, they can trigger waves of star formation in Messier 87, compressing gas clouds and igniting the birth of new stars. These smaller galaxies also serve as cosmic time capsules, preserving ancient stars and structures that offer clues about the early universe. By studying these dwarf companions, astronomers can piece together the history of Messier 87 and understand how it grew into the giant we see today. One of the most intriguing aspects of these dwarf galaxies is their diversity. Some are compact and densely packed with stars, while others are diffuse and spread out, almost ghostly in appearance. This variety hints at different origins and evolutionary paths, adding layers of complexity to the story of Messier 87 galactic neighborhood. Each dwarf galaxy tells a unique tale, whether it's a relic from the early universe or a fragment of a larger galaxy torn apart by gravitational forces. As we continue to explore Messier 87, these dwarf galaxy companions remind us that even the smallest players can have a profound impact on the cosmic stage. Their interactions with Messier 87 not only shape the galaxy's structure but also enrich its history, offering a glimpse into the dynamic processes that drive galactic evolution. Next, we'll turn our attention to another high-energy phenomenon in Messier 87, the occasional gamma-ray bursts that light up the galaxy with incredible intensity. Now, let's dive into one of the most explosive phenomena in the cosmos: gamma-ray bursts. These fleeting yet incredibly powerful bursts of energy are some of the most energetic events in the universe, and Messier 87 has been no stranger to their dazzling displays. Detected occasionally near this massive galaxy, gamma-ray bursts are like cosmic fireworks, lighting up the darkness with unimaginable intensity. Gamma-ray bursts originate from some of the most extreme environments in the universe. They are often linked to the collapse of massive stars known as hypernova or the collision of neutron stars. When these cataclysmic events occur, they release an enormous amount of energy in the form of gamma rays, the most energetic form of light. These bursts are so powerful that, for a brief moment, they can outshine entire galaxies, including Messier 87 itself. But what makes gamma-ray bursts near Messier 87 particularly fascinating is their connection to the galaxy's supermassive black hole and its surrounding environment. While most gamma-ray bursts occur in distant galaxies, the ones detected near Messier 87 offer a unique opportunity to study these high-energy events in a galaxy with such a well-known and active core. The presence of the black hole and its relativistic jet could play a role in triggering or influencing these bursts, adding another layer of complexity to their origins. The significance of gamma-ray bursts extends far beyond their spectacular light shows. They serve as cosmic laboratories, allowing scientists to probe the most extreme conditions in the universe. By studying these bursts, astronomers can learn about the behavior of matter and energy under conditions that are impossible to replicate on Earth. They also provide clues about the early universe, as some gamma-ray bursts are thought to originate from the deaths of the first generation of stars. In the context of Messier 87, gamma-ray bursts offer a window into the high-energy processes that shape the galaxy. They highlight the dynamic and often violent nature of the universe, reminding us that even in a galaxy as massive and seemingly stable as Messier 87, explosive events are always just around the corner. As we continue to explore this cosmic giant, these bursts serve as a reminder of the incredible forces at play in the universe. Next, we'll explore another invisible yet powerful force shaping Messier 87. The complex magnetic fields that weave through the galaxy, influencing everything from its structure to its relativistic jet. Now, let's turn our attention to another invisible yet incredibly powerful force at work in Messier 87, the magnetic fields. These intricate webs of magnetic energy are woven throughout the galaxy, playing a crucial role in shaping its most dramatic features, including the famous relativistic jet. While we can't see magnetic fields directly, their influence is undeniable, and they are key to understanding how Messier 87 operates on a grand scale. Magnetic fields in Messier 87 are not just simple lines of force, they are complex, dynamic structures that interact with the galaxy's gas, dust, and even its supermassive black hole. One of their most striking effects is on the relativistic jet, the powerful stream of particles shooting out from the black hole at nearly the speed of light. These magnetic fields act like a cosmic funnel, channeling and accelerating the jet's particles, giving it the incredible energy and direction we observe. Without these fields, the jet might not exist in its current form, or it could be far less focused and powerful. But the influence of magnetic fields doesn't stop at the jet. They also play a significant role in shaping the overall structure of Messier 87. By interacting with the galaxy's gas and dust, magnetic fields help regulate the flow of material toward the black hole, influencing how it grows and evolves. They can even affect the formation of stars, either by compressing gas clouds to trigger star birth or by preventing collapse in certain regions. This delicate balance makes magnetic fields a key player in the galaxy's life cycle. What makes Messier 87 magnetic fields particularly fascinating is their sheer scale. They extend far beyond the galaxy's core, intertwining with the surrounding intergalactic medium. This means their influence isn't confined to Messier 87 alone. They can affect neighboring galaxies and the vast cosmic web that connects them. Studying these fields gives astronomers a deeper understanding of how galaxies interact and evolve over billions of years. As we continue to unravel the mysteries of Messier 87, magnetic fields stand out as a vital piece of the puzzle. They remind us that even the forces we can't see play a profound role in shaping the universe. Next, we'll journey into the ancient past of Messier 87 as we explore its oldest star clusters, relics from the early days of the cosmos. Now, let's step back in time to uncover one of the most ancient treasures hidden within Messier 87, its oldest star clusters. These clusters are like cosmic time capsules, preserving secrets from the early days of the universe. Scattered throughout the galaxy, these ancient groupings of stars are not just beautiful to observe, they are also key to understanding how galaxies like Messier 87 formed and evolved over billions of years. The star clusters in Messier 87 are among the oldest known in the universe, with some estimated to be nearly as old as the universe itself, around 13 billion years. To put that into perspective, these clusters were already ancient when our own solar system was just beginning to take shape. Their age makes them invaluable to astronomers, offering a glimpse into the conditions of the early cosmos and the processes that shaped the first galaxies. What makes these clusters so fascinating is their composition. Unlike younger star clusters, which often contain a mix of stars of varying ages, these ancient clusters are made up almost entirely of old, metal-poor stars. This tells us that they formed during a time when the universe was still young and heavy elements like iron and gold were scarce. By studying these stars, scientists can piece together the chemical history of the universe and learn how elements essential for life were gradually forged in the hearts of stars. But the story doesn't end there. These ancient star clusters also provide clues about the formation of Messier 87 itself. Many of them are thought to have formed in smaller galaxies that were later absorbed by Messier 87 as it grew over time. This process, known as galactic cannibalism, is a common way for large galaxies to accumulate stars and other material. By tracing the origins of these clusters, astronomers can map out the history of Messier 87 growth and its interactions with neighboring galaxies. The sheer number of these ancient clusters in Messier 87 is another remarkable feature. While most galaxies have a few hundred globular clusters, Messier 87 boasts thousands, making it one of the richest collections in the known universe. This abundance suggests that Messier 87 has had a particularly active history of mergers and acquisitions, gobbling up smaller galaxies and their star clusters over billions of years. As we study these ancient star clusters, we're not just looking at the past, we're also gaining insights into the future. Their stability and longevity offer a glimpse of what might happen to star clusters in other galaxies, including our own Milky Way, over the course of cosmic time. Next, we'll shift our focus to the vast reservoirs of intergalactic gas surrounding Messier 87 and how they contribute to the galaxy's ongoing growth and evolution. Now, let's turn our attention to the vast, invisible ocean that surrounds Messier 87, the intergalactic gas. This immense reservoir of gas stretches far beyond the galaxy's visible boundaries, playing a crucial role in its growth and evolution. While it might not be as flashy as a supermassive black hole or as mysterious as dark matter, this gas is a key ingredient in the cosmic recipe that keeps Messier 87 thriving. The intergalactic gas surrounding Messier 87 is primarily composed of hydrogen and helium, the simplest and most abundant elements in the universe. But don't let its simplicity fool you. This gas is anything but ordinary. It's incredibly diffuse, meaning it's spread out over vast distances, yet it holds enough material to fuel the formation of new stars and even entire galaxies over time. This gas doesn't just sit idly by. It's constantly being pulled into Messier 87 by the galaxy's immense gravitational pull, feeding its growth like a cosmic conveyor belt. So, where does this gas come from? Much of it is thought to be leftover material from the early universe, remnants of the Big Bang that never condensed into stars or galaxies. Over billions of years, this gas has been drawn into the gravitational wells of massive structures like Messier 87, where it accumulates and contributes to the galaxy's ongoing development. Some of it may also come from smaller galaxies that have been torn apart by Messier 87 gravity, their gas stripped away and absorbed into the larger galaxy's reservoir. One of the most fascinating aspects of this intergalactic gas is how it interacts with Messier 87 supermassive black hole. As the gas falls toward the galaxy's center, it can become superheated, emitting intense radiation and even feeding the black hole's accretion disk. This process not only powers the black hole but also influences the galaxy's overall structure, shaping the flow of gas and the formation of new stars. But the story doesn't end there. This gas also plays a critical role in the galaxy's future. As Messier 87 continues to grow, it will draw in more and more of this intergalactic material, potentially triggering new bursts of star formation and further shaping its evolution. In a sense, this gas is the lifeblood of the galaxy, ensuring that Messier 87 remains a dynamic and ever-changing cosmic entity. As we explore the mysteries of Messier 87, it's clear that even the seemingly mundane elements like intergalactic gas hold profound significance. Next, we'll dive into the swirling chaos of the black hole's accretion disk, where the galaxy's most energetic processes unfold. Now, let's zoom in closer to the heart of Messier 87, where chaos and creation collide in a spectacular display of cosmic power, the black hole's accretion disk. This swirling maelstrom of matter is one of the most dynamic and energetic regions in the entire galaxy, and it's here that the supermassive black hole exerts its most dramatic influence. The accretion disk is essentially a vast, spinning ring of gas, dust, and other material that orbits the black hole at incredible speeds. As these particles spiral inward, they don't just fall straight into the black hole. Instead, they form a disk-like structure, heated to extreme temperatures by the immense gravitational forces at play. Temperatures in the inner regions of the disk can reach millions of degrees, causing the material to glow brightly across the electromagnetic spectrum, from radio waves to X-rays. But what makes this disk so fascinating isn't just its heat or its glow, it's the sheer amount of energy it generates. As the material in the disk spirals closer to the black hole, it loses gravitational energy, which is converted into heat and radiation. This process releases staggering amounts of energy, making the accretion disk one of the most luminous objects in the universe. In fact, the light and radiation emitted by the disk can outshine the entire galaxy, illuminating the surrounding space and influencing the formation of stars and other structures. The accretion disk also plays a critical role in powering the black hole's relativistic jet, the high-speed stream of particles we explored earlier. Some of the material in the disk doesn't fall into the black hole but is instead funneled along magnetic field lines and ejected at nearly the speed of light. This process not only fuels the jet but also helps regulate the flow of matter into the black hole itself, creating a delicate balance between consumption and expulsion. Interestingly, the accretion disk isn't uniform. Its structure can vary depending on factors like the black hole's spin, the amount of material available, and even the presence of magnetic fields. In some regions, the disk may be thin and smooth, while in others it can become turbulent and clumpy, with pockets of material colliding and interacting in unpredictable ways. These variations can lead to fluctuations in the disk's brightness and energy output, making it a dynamic and ever-changing feature of Messier 87. As we peer into this swirling vortex of matter, we're reminded of the incredible forces at work in the universe. The accretion disk isn't just a byproduct of the black hole's gravity, it's a powerhouse that drives the galaxy's most energetic processes, shaping its evolution and illuminating the mysteries of the cosmos. Next, we'll explore how Messier 87's immense gravity bends the very fabric of space-time, creating fascinating distortions known as gravitational lensing. Now, let's shift our focus to one of the most mind-bending phenomena in the universe: gravitational lensing. Messier 87's supermassive black hole isn't just a cosmic vacuum cleaner. Its immense gravity warps the very fabric of space-time, bending light from distant objects in ways that challenge our understanding of reality. This effect, known as gravitational lensing, acts like a natural telescope, magnifying and distorting the light of galaxies and stars that lie far behind Messier 87. Imagine space-time as a giant, stretchy sheet. When you place a massive object like Messier 87 black hole on this sheet, it creates a deep well curving the fabric around it. Light traveling through this warped space doesn't move in a straight line, it follows the curve, bending around the black hole. This bending can create multiple images of the same distant object, or even stretch it into arcs and rings like a cosmic funhouse mirror. These distortions aren't just visually stunning, they're also incredibly useful for astronomers. Gravitational lensing allows scientists to study objects that would otherwise be too faint or distant to observe. By analyzing the distorted light, researchers can measure the mass of Messier 87 black hole and the surrounding dark matter halo with remarkable precision. It's like using the galaxy's gravity as a magnifying glass to peer deeper into the universe than ever before. In some cases, lensing has even revealed galaxies that formed just a few 100 million years after the Big Bang, offering a glimpse into the early stages of cosmic history. But the effects of gravitational lensing go beyond just magnification. The way light bends can also reveal the distribution of dark matter in Messier 87. Since dark matter doesn't emit light, its presence is usually inferred through its gravitational effects. Lensing provides a direct way to map this invisible material, helping astronomers piece together the galaxy's structure and evolution. It's a powerful tool that bridges the gap between the visible and the unseen, unlocking secrets that would otherwise remain hidden. What's truly fascinating is how gravitational lensing can create what's known as an Einstein ring. When a distant object, the lensing galaxy, and the observer are perfectly aligned, the light from the background object forms a complete circle around the lens. Messier 87's immense gravity makes it a prime candidate for producing these rare and beautiful phenomena. These rings aren't just cosmic curiosities, they provide precise measurements of the lensing galaxy's mass and the geometry of the universe itself. As we marvel at the strange and beautiful distortions created by Messier 87 gravity, we're reminded of how interconnected the cosmos truly is. Gravitational lensing isn't just a quirk of physics, it's a window into the universe's deepest mysteries, from the nature of dark matter to the origins of galaxies. Next, we'll dive into the high-velocity gas clouds near the galaxy's center, where the black hole's influence creates yet another layer of cosmic intrigue. Now, let's zoom in closer to the heart of Messier 87, where chaos and speed reign supreme. Near the galaxy's center, astronomers have discovered something extraordinary: high-velocity gas clouds racing through space at mind-blowing speeds. These clouds aren't just drifting aimlessly, they're caught in a cosmic tug-of-war with the supermassive black hole, creating a dynamic and turbulent environment. These gas clouds are moving so fast that they can reach speeds of thousands of kilometers per second. To put that into perspective, that's fast enough to travel from Earth to the Moon in just a few minutes. But what's propelling them to such incredible velocities? The answer lies in the immense gravitational pull of the black hole. As these clouds get too close, they're whipped around like leaves in a hurricane, accelerated to extreme speeds before being flung outward or swallowed entirely. The origins of these high-velocity gas clouds are still a bit of a mystery. Some scientists believe they could be remnants of smaller galaxies that were torn apart by Messier 87 gravity, their gas stripped away and now swirling around the black hole. Others suggest they might be the result of violent collisions between stars or even outflows from the black hole's accretion disk. Whatever their source, these clouds are a testament to the chaotic and energetic processes happening at the galaxy's core. What's truly fascinating is how these gas clouds interact with the black hole. As they spiral inward, they don't just disappear quietly. Instead, they heat up to incredible temperatures, emitting intense radiation that can be detected across the electromagnetic spectrum. This radiation provides astronomers with valuable clues about the black hole's environment, from the density of the gas to the magnetic fields that shape its flow. In some cases, the gas clouds can even trigger bursts of activity, causing the black hole to flare up as it devours its cosmic meal. But not all of the gas is destined to fall into the black hole. Some of it is ejected outward at high speeds, creating powerful winds that can influence the surrounding galaxy. These outflows can sweep away star-forming material, effectively putting the brakes on new star formation in certain regions. It's a cosmic balancing act. While the black hole consumes, it also shapes the galaxy around it, regulating its growth and evolution. The high-velocity gas clouds near Messier 87 Center are more than just a spectacle. They're a window into the complex interplay between gravity, gas, and radiation. By studying these fast-moving clouds, scientists can piece together the story of how supermassive black holes shape their galaxies, from the smallest scales to the largest. Next, we'll explore the mysterious starless regions of Messier 87, where the absence of stars raises even more intriguing questions about the galaxy's structure and history. Now, let's shift our gaze to one of the most puzzling features of Messier 87, the starless regions. These vast, dark areas scattered throughout the galaxy stand out starkly against the backdrop of its bustling stellar neighborhoods. Unlike the rest of Messier 87, which is teeming with stars, these regions are eerily empty, raising questions about what could be suppressing star formation or clearing out existing stars. One possible explanation for these starless zones lies in the galaxy's supermassive black hole. The immense gravitational forces and energetic outflows from the black hole could be sweeping through these regions, stripping away the gas and dust needed to form new stars. Without this raw material, star formation grinds to a halt, leaving behind a cosmic void. Additionally, the powerful winds generated by the black hole's activity might have pushed existing stars out of these areas, creating the barren patches we observe today. Another theory points to the role of dark matter. While dark matter itself doesn't emit light or interact with ordinary matter in the same way, its gravitational influence could be shaping these regions. If dark matter is distributed unevenly, it might create pockets where the gravitational pull is too weak to hold onto stars or the gas needed to form them. This uneven distribution could explain why some parts of Messier 87 are densely packed with stars while others remain eerily empty. There's also the possibility that these starless regions are the aftermath of galactic collisions. Messier 87 is known to have absorbed smaller galaxies over billions of years, and the gravitational chaos from these mergers could have disrupted star-forming processes in certain areas. The violent interactions might have scattered stars and gas, leaving behind these mysterious voids. Over time, the galaxy's structure could have stabilized, but the scars of these ancient collisions remain visible as starless regions. What makes these areas even more intriguing is their potential to teach us about the broader processes at work in galaxies. By studying why stars are absent in these regions, astronomers can gain insights into the delicate balance between star formation, galactic dynamics, and the influence of supermassive black holes. These starless zones are not just empty spaces, they're clues to understanding how galaxies evolve and change over time. As we continue our journey through Messier 87, we'll next turn our attention to the cosmic ray accelerators hidden within this galaxy, where particles are hurled through space at nearly the speed of light, revealing yet another layer of its cosmic complexity. Now, let's venture into one of the most energetic phenomena in Messier 87, the cosmic ray accelerators. These powerful mechanisms are responsible for hurling particles through space at nearly the speed of light, creating some of the most extreme conditions in the galaxy. But what exactly are cosmic rays, and how do they reach such incredible speeds within Messier 87? Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at astonishing velocities. In Messier 87, these particles are accelerated by the galaxy's supermassive black hole and its relativistic jet. As material spirals into the black hole, it generates immense magnetic fields and shock waves. These forces act like natural particle accelerators, boosting cosmic rays to near-light speeds and launching them into the surrounding space. the impact of these cosmic rays is profound. As they travel outward, they collide with gas, dust, and other particles, creating secondary particles and radiation. These interactions can heat up the surrounding material, influencing the temperature and dynamics of the galaxy's environment. In some cases, cosmic rays can even trigger star formation by compressing gas clouds, though their intense energy can also disrupt star-forming regions, adding another layer of complexity to the galaxy's evolution. What makes Messier 87 cosmic ray accelerators particularly fascinating is their connection to the galaxy's most extreme features. The relativistic jet, for instance, not only propels cosmic rays but also channels them into focused beams that extend far beyond the galaxy itself. These beams can travel millions of light years, impacting the intergalactic medium and even reaching other galaxies. This makes Messier 87 a key player in understanding how cosmic rays shape the universe on a grand scale. Studying these accelerators also provides insights into the origins of cosmic rays in other parts of the universe. By observing how they behave in Messier 87, astronomers can piece together the processes that generate these high-energy particles in other galaxies and even in our own Milky Way. It's a reminder that even the smallest particles can have a massive impact on the cosmos. As we continue to unravel the mysteries of Messier 87, our next stop will take us to the strange, unidentified radio sources detected near this galaxy. These enigmatic signals add yet another layer of intrigue to this already fascinating cosmic giant. Now, shifting our focus to another intriguing mystery, we arrive at the unidentified radio sources near Messier 87. These enigmatic signals have puzzled astronomers for years, as their origins remain shrouded in uncertainty. Unlike the cosmic ray accelerators we just explored, these radio sources don't neatly fit into any known category of cosmic phenomena. They emit bursts of radio waves that defy easy explanation, leaving scientists to wonder what could be producing them. One possibility is that these radio sources are linked to the supermassive black hole at the heart of Messier 87. The black hole's immense gravitational pull and the chaotic environment around it could generate unusual radio emissions. For instance, interactions between the black hole's accretion disk and nearby gas clouds might create bursts of energy detectable as radio waves. However, the patterns of these emissions don't fully match what we'd expect from such interactions, leaving room for alternative theories. Another idea is that these signals could come from objects we've yet to discover or fully understand. For example, they might originate from exotic stellar remnants such as neutron stars or black holes with unusual properties. Alternatively, they could be the result of interactions between Messier 87 and its smaller companion galaxies, which might produce radio emissions as they exchange material or collide. Yet, without more data, these explanations remain speculative. What makes these radio sources particularly fascinating is their unpredictability. Unlike the steady emissions from known objects, these signals appear sporadically and vary in intensity. This irregularity makes them difficult to study and even harder to classify. Some astronomers have suggested that they could be evidence of entirely new astrophysical processes, ones that challenge our current understanding of how the universe works. Despite the mystery, studying these radio sources offers valuable insights. By analyzing their properties, astronomers can refine their models of how radio emissions are generated in extreme environments. This, in turn, could help us better understand similar signals detected in other galaxies, potentially unlocking new secrets about the cosmos. As we wrap up our journey through the strange and wondrous objects of Messier 87, these unidentified radio sources serve as a fitting reminder of how much we still have to learn about the universe. They challenge us to keep exploring, questioning, and pushing the boundaries of our knowledge. And with that, we conclude our exploration of the 25 strange objects in this incredible galaxy, leaving you with a sense of awe for the mysteries that still await discovery. As we bring our journey through the wonders of Messier 87 to a close, it's impossible not to feel a profound sense of awe. From the supermassive black hole at its core to the mysterious radio sources that defy explanation, this galaxy has revealed a universe teeming with strangeness and beauty. Each of the 25 objects we've explored, whether it's the relativistic jet, the dark matter halo, or the ancient star clusters, has offered a glimpse into the incredible complexity of the cosmos. Together, they paint a picture of a galaxy that is not only a cosmic powerhouse but also a treasure trove of scientific discovery. Messier 87 challenges us to rethink what we know about the universe. Its supermassive black hole, the first ever to be imaged, has reshaped our understanding of gravity and space-time. The galaxy's elliptical shape, its swarm of globular clusters, and its ghostly ultra-diffuse galaxies all tell a story of cosmic evolution on a grand scale. And then there are the mysteries, the unidentified radio sources, the fast-moving stars, and the starless regions that remind us how much we still have to learn. These objects aren't just curiosities, they're keys to unlocking the secrets of the universe. What makes Messier 87 so special is its ability to inspire. It's a reminder that the universe is vast, dynamic, and full of surprises. Every discovery we make here deepens our understanding of not just this galaxy, but the entire cosmos. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. And as we continue to study Messier 87, we're sure to uncover even more wonders that will challenge and amaze us. Before we go, we'd love to hear your thoughts. Which of these strange objects fascinated you the most? Do you have a theory about the unidentified radio sources or the starless regions? Share your ideas in the comments below. We're excited to hear your perspectives. And if you enjoyed this journey through the mysteries of Messier 87, don't forget to hit the like button, subscribe to the channel, and ring the notification bell so you never miss out on our next cosmic adventure. The universe is full of wonders, and we can't wait to explore them with you. Until next time, keep looking up.